lower. They're out of water, the temperature lowers, but we just put the number in for what it was in water. So my so the real number is going to be a little bit lower.
Exactly.
I wrote it out for you. That's what you have written down right there.
Yeah, well,
All crossed out? Oh, yeah.
no, what I have crossed out, I don't even know. What
So our number.
I pretty much just stated exactly what this stated. I say it's garbage. I mean,
It's garbage.
It's useless.
All right, I'm gonna fill my water and then we'll get started.
But yeah, because so the real number is going to be lower, so our number goes higher.
Okay.
So the real number is lower. I think it's asking for the real number.
It's asking. Wait, so it's asking for the actual number, not ours. Is it asking for what we have?
It doesn't matter what metal it is.
Or is
It's
it asking
asking
for what the actual thing is?
It doesn't matter. It doesn't matter.
I hate this
Just
question.
a matter. Any substance in there. If you move it out of the heat, it's going to lose. It doesn't matter which one it is.
Huh. You remove it.
Yes. So we took the what is in the thing, but only moved it and lost in time. Yeah.
There's air at last.
Yeah, it's going to cool off a little bit. That's why we had to pour it fast
Yeah.
to lose as little as possible. But we did lose some, but we didn't put in that amount that we lost.
It'll be lower because it puts heat on it's right.
Yes. But we didn't calculate for that. We couldn't.
Yes, yes. Yeah, exactly. Yeah. Yeah. I can show mathematical proof afterwards if you want, but yeah, Hunter nailed it. Yeah, yeah. Just show the variables and just point like smaller than written. Reality is smaller than what we wrote. Yeah. Yeah. You know, fine, we'll do it right now. So like C negative MH2O, CH2O, delta TH2O. This is C of like the beads, right? And then you have M beads, delta T beads. Okay. So you're gonna plug in a delta T here of, I don't know, like 50-ish, 40 or 50-ish. Okay. Is as written. Okay, delta T reality. I don't know, it could be like 45, or let's just say 40 as really extreme. It's not gonna be that bad, but you can see that in reality, that denominator should be smaller, and therefore we should get a bigger number because of that. Yeah, just keep it to math. Explain everything with math, and then you're done. Yeah. No. He did in his own way. He did. I've had many years of training to hone my explanations. Yeah. So there you go. You want the explanation, then here it is. Oh, I almost got fired. I almost got fired. Okay. All right. I start coaching baseball next week, so there's my training. Okay. All right. Happy Friday. Let's see. Today's quiz I have it due tomorrow. Last week's quiz I extended it to tomorrow because a lot of people messed up on it. I said, sure, why not? Last week's homework I extended to tomorrow. It's raining extensions, but hopefully people take advantage of that and do well. All right. Let's just dive right on in. All right, we're continuing with the topic of heat. Okay. Last class was kind of more qualitative in nature. We were talking about man, what were we talking about? Let me pull it up. Oh, we were talking about heat versus temperature, right? And then we were all that stuff. Okay. Today we're going to get into the calculation side of things. A little bit more theory, but mostly today's a calculation sort of day. Okay. And the main thing we're going to be studying today is water. Okay, so we're going to make an H2O phase diagram. And for this diagram, you'll maybe want at least half of a page. Okay, course, I like to take a whole page. We're going to just make a nice big old graph here. Okay. And we're going to talk about the behavior of water depending on the temperature. Okay. Basically, the sort of question we're going to try to ask today is like, to take water to its boiling point, how much heat does the water need to absorb? To melt some ice, how much heat does the water need to absorb? You know, those sorts of questions. And we're going to calculate those answers, okay? Now, because water can go through 3 different phases of matter, we're going to have to tune our calculation based off of the phase of matter. Okay, so this is what this phase diagram is going to help us out with. Okay, all right. So what we're going to do is we're going to make a chart. That looks like that. Okay, and I'm going to divide the chart into 5 sections. Let me take my jacket off. Okay, so section number 1, we can see we have this steep slope. Section 2 is completely flat. Okay. Section 3, we have a slope again. And if you want, you can draw that second slope to be not as steep as the first slope. Okay. The 4th section is flat again, and for a longer distance. And then we have this 5th section. Okay. So 5 different sections: slope, flat, slope, flat, slope. Okay. All right. We got an x-axis of Q for heat. And then we have a y-axis T for temperature. Okay. And we'll explain these shapes in a moment. Y, slope, flat, slope, flat, slope. And I meant for this to be flat. It looks like I put an accidental curve into it. I want it to be flat. Let's see if we can make that a little better. Flat. Okay. So we're going to try to make sense of the strange looking shape today. Okay, maybe it's a ski hill. Okay. And then we have this flat zone, and then I was an okay skier as a kid, not great. Okay, and I'm just going to look for people's pens being down before we continue. Okay. If you're done already, you can start to guess what each region means. Okay, so let's put in some labels. This label right here, the very lowest temperature possible, physically possible, is negative 273.15. And let's stay in Celsius today. Degrees Celsius. That's 0 kelvins, absolute 0, but Celsius is easier. So negative 273.15. All right, so what do we know about water at negative 273.15? What we know about water is it's ice at that point. It's frozen solid as ice, okay? And when you have ice, you have hexagonal or sometimes pentagonal channels, okay? And you don't have a lot of vibration going on in the ice. And so that means your water molecules are locked into place, okay? To describe that physically, we're going to have to talk about something called a hydrogen bond. A hydrogen bond is an attractive force between individual water molecules. It's when a hydrogen points at another oxygen, okay? In 4 to 5 weeks, we're going to talk about intermolecular interaction, the forces of nature that hold molecules together. And the strongest intermolecular interaction of them all is a hydrogen bond, okay? As we'll study 4 or 5 weeks from now, hydrogen has a little bit of a positive charge on it, actually, because oxygen is stealing it away. We talked about that electronegativity, okay? And so we have slightly positive hydrogens pointing to slightly negative oxygens. And this hydrogen bond keeps this water structure locked into place, okay? So that's true when water is cold, okay? Now, I heat up this ice. Everything's going to start to vibrate and vibrate more and more and more as I add more heat. Okay, I'm heating it up. Okay, I'm blowing a fire at it or something. And it will keep vibrating more and more until something happens. Okay. And what happens to water at 0 Celsius? We notice a change in the behavior of water. And here's 0 Celsius. Okay. So we got these molecules of water vibrating. The OH bonds are vibrating. There's not too much rotation because it's rigid. And there's no translations because everything's locked into place. Mostly vibration. I'd say 80, 90% vibrations, 10, 20% rotations. But what do we know about water at 0 Celsius? What if I go beyond 0 Celsius? Don't overthink this. What happens past 0 Celsius? Your water is now liquid, okay? Melted, good. Synonyms, right? We're on the same page, right? And look, why is water denser when it's a liquid? Those little channels get destroyed, okay? Those little channels get destroyed, and so the water becomes denser. That's the opposite of most solid and liquid that we know of. Things expand normally as they vibrate, but for water, you loosen those hydrogen bonds, and they're still there, but everything's kind of just floppy, okay? You change hydrogen bonding partners every fraction of a second, and so you just have this messy, chaotic soup. And that's what liquids are. They're messy, chaotic soups, okay? This loosening of hydrogen bonds begins at 0 Celsius. And that's the definition of melting. The definition of melting is the loosening of intermolecular interactions, okay? Now check this out. During the melting phase, water stays, the ice block stays the same temperature, okay? Now you may be thinking, okay, if you're melting ice, it can't really all stay at the same temperature, okay? You're going to melt that ice, you're going to have a puddle of water in the sides, and that water is going to start to heat up. And you're right, okay? But if you do this process like at an infinitesimally slow pace, or maybe more realistically, we crush the ice into a powder, okay? And we were constantly stirring. Then with the temperature probe put into the cup, you would notice that the temperature more or less stays plateaued, okay? That's because the process of melting is called a latent heat process. You don't need to write that. I'm not going to put it on a test, but for the handful of you that will have to go on to further engineering or physics, they'll talk about latent heat processes. Okay, latent means slow, delayed, or something you don't really notice. Okay, so the reason why we call melting a latent heat process is we don't notice a temperature change, even though it is absorbing heat. Okay, it's absorbing heat, but we don't notice it absorbing heat. Well, you kind of do if you look at the atomic molecular structure. Those hydrogen bonds are breaking and it's becoming a soup, okay? So in other words, instead of the temperature going up, the energy that you're putting in as heat is directed. It's being used to loosen those hydrogen bonds. And that's why we don't see the temperature going up. The vibrations aren't getting stronger, but we're just loosening things, okay? Once you have melted every last piece of ice and it's all liquid water, the temperature can begin to climb again. Okay, so let's start labeling these. Okay, this first domain is the ice domain. Okay, and you can heat ice. Or you can cool the ice, chill it. Okay. And when you're putting heat into a system, okay, when you're shoving heat into a system, you're going to have positive Q values, and that's going to be endothermic. Okay. If you've never seen or heard that word before, let me spell it out. Endothermic. Endo means internal. Thermic means heat. Okay. So that means you have something absorbing heat. You're going to have a positive Q. You have gained more heat energy than you started out with. If you're going in the other direction, you're going to have negative Q, which is called exothermic. Okay. Same words as biology. Like you have an endoskeleton. We have skeletons on the inside of our body, but some creatures have an exoskeleton. I don't know, like a crab or something. I don't know. I was a BC student in biology, but yeah, crabs have hard stuff on the outside. Maybe that's an exoskeleton. I don't know. Okay. Endo versus exo. Okay. So we can heat, cool ice. There's temperature changes associated with that. And right here, this is, if we're going in this direction, we are melting. And if we're going in the other direction, removing heat, then we are freezing. Okay. Now, in some sciences, chemistry included, some people will use the term fuse instead of freeze. Okay. When you freeze something, you're fusing things together. Okay. And when we're talking about phase changes, it seems like most textbooks like to use the word fuse more than freeze, which is kind of weird. Freeze is like the everyday word, just use that. But nope, they say fusion. Fusion makes me think of jazz, but nope, we're talking about fusing objects. Okay. So we have the ice domain. Okay. We have the melting domain. The next domain we're going to talk about, I'm going to use green here. Okay. This is, I can't just say water anymore. Normally, when we just say water, we're talking about liquid water, but water just means H2O. So I'm going to say liquid water here. Okay. Water as we usually know it, and we can heat and we can cool. Same idea. Okay. And the temperature will begin to climb again. Okay. All right. Liquid water, we can heat it, we can cool it, but we see if we continue to add more heat, we suddenly have a temperature that is constant again. Okay. What do we know about water? You heat it until you see something happening, boiling, and we know water boils at that one, 100 Celsius. Okay. Good. Okay. You get this plateau of temperature again. It's another latent heat process. Okay. Instead of the temperature increasing, we see that the temperature is a stable reading for the water that's boiling. Okay. That's because each water molecule that absorbs excess heat is now turning into water vapor. Okay. Instead of its vibrational energy getting higher, that excess energy is going into breaking the hydrogen bond and releasing the water entirely from the bulk. Okay. And this will just keep happening until every single water molecule has intermolecular separation. Once you have intermolecular separation, then you now have steam, and that steam can then heat up further. Okay. But in order to get steam, you need so much heat in each water molecule that if it were to even attract for a brief moment, it has enough jiggliness in it to just bounce right off. And you need a decent amount of heat because water is really sticky unto itself. Okay. So you need to get it quite hot. All right. How hot? You need a lot of energy. Notice how much heat we have here. It's the widest of all of our domains. Okay. So let's label this one. Okay. We are, if we're going to the right, we are vaporizing, aka boiling. Okay. And here's a word maybe we haven't used in a while. What's the opposite of vaporization? Going from a gas back to a liquid. We see it on our cars often in the morning. Well, at the moment, the condensation, right? Our mornings are so cold that condensation turns into ice. It freezes. Some of it is a straight sublimation, in fact. Subliming, subliming is going straight from solid to gas. That's called sublimation. Here, if you want to write that down somewhere. Going straight from solid to gas is called sublimation, or to sublime. And going from gas back to solid is called deposition. Okay, not a common word. We're not going to talk too much about sublimation and deposition. Just know that it exists. Water can actually also supply or deposit. Okay. I don't know if you've seen those viral YouTube videos. Someone takes their boiling water and then they like kind of throw it into the air, and they're like Siberia or something, and you see it mist. There you see water turning to ice, but you have vapor of water at the top, and that's turning to ice. So you kind of see sublimation there. Okay. No, sorry, deposition, excuse me. If you had a block of ice and you throw it onto something insanely hot, like insanely hot, you're going to get some sublimation. But deposition, anyone heard of chemical vapor deposition, especially for those interested in engineering? Chemical vapor deposition. Okay, so CVD, this is a very industrially important process. Anyone heard of like powder coating maybe? Okay, it's somewhat similar. Powder coating, it might be a chemical vapor deposition, or you might have superfine particles of paint or whatever you're coating with. But in chemical vapor deposition, you heat something insanely hot. Okay, you don't have to draw this, but you have let's talk about making diamonds. Okay, you have a carbon source, you get it so insanely hot and you have nothing else around, so it can't turn to carbon dioxide. Okay, and then you have carbon atoms floating around as gas. And if you're growing a lab diamond, these will deposit straight from gas to solid onto this chilled diamond nucleus. So super hot source, you atomize, and it goes, since it's ultra cold, straight from gas to solid. And if you do this really slow and controlled, that diamond will grow perfectly. Okay. And that's how lab-made diamonds are used or made. Of course, that's increased in the jewelry sector, but the vast majority of this is used so you can make like diamond-coated saw blades and sandpapers and what have you for construction purposes. Okay. All right. Anyway, but let's go back to water. Okay, you've steamed up all the water, so now we have water vapor, aka steam, at the top. And steam can then be heated up further or cooled down. Okay. And there's our phase diagram. All right, we're gonna write a few more details on this, but the main thing I want you to see is water has 3 distinct phases. Most things have 3 distinct phases of solid, liquid, gas. Okay. There's a few things that will lack a phase. For example, something you get at a grocery store like Winco occasionally. You have a long trip. You need to keep something cold. You go for the dry ice. Okay. Dry ice sublime straight from solid to gas. Okay. And vice versa if you want to cool it down. Okay, dry ice is dangerous in a car. There's no warning sign that there's no like puddle like, oh, it's melting. You don't get any of that. It goes straight to a gas. So what do you do if you have dry ice in the car and you have a long road trip? So you don't asphyxiate. Open a window. Okay, so you don't have a buildup of CO2. All right. Or at the very least, you run air conditioning that is pulling outside air in rather than recycling the same air. Okay. For me, I just play it safe. I'll just crank open a window a little bit. I don't have to do that too often. All right. So that's the phase diagram. Now, I said we're doing calculations today. So now we need some numbers. Okay. Let's start out with the liquid water that we already know. Okay. Let me go to a scratch paper for a moment. Okay. Anyone remember the specific heat capacity of water? Those who had lab, we all had lab already this week. We use it a million times, right? So for liquid water, that specific heat was what? Yeah, it's 1. And it's actually 1 forever, okay? Calories per gram degrees Celsius. Okay, here's the history of the calorie, okay? To heat up water, it's observed you need 4.184 joules to take 1 gram of water up by 1 degree Celsius. That's the observation. I don't remember the name, but eventually someone got tired of writing 4.184 all the time. They said, yo, let's just call this number a 1, and we'll just call it a calorie, okay? And thus the calorie was born, so we could have a specific heat of exactly 1, okay? But most textbooks, including ours, and most homework packages, including ours, when it comes to phases of water, they prefer to use joules instead of calories for some reason. So we're going to stick with joules today, which means we're going to grab this one. Okay. So the C of liquid H2O is 4.184 joules per gram degrees Celsius. Okay, go ahead and write that one down. Okay. And no, you don't need to memorize that. I would provide that on an exam. Nothing today has to be memorized. I provide the equations and constants on the exams. So this would be exam 3, okay, after spring break. Okay. Let's get our next value. All right. If we're going to, let's go this leftward direction first. If we're going to freeze the water, we're going to fuse it together. It's going to release energy. If you melt something, it absorbs energy. If you freeze something, it therefore does the opposite, which is release energy. Okay. The value we need is not a C, but it's called an H. You're going to see when we do the math today why it's an H and it's not a C. H is going to be for the phase changes. And this is called an H of fusion, F-U-S. Okay. The fusion of water, H2O, H fusion water is 6.01 kilojoules. So not joules, but kilojoules. And that's going to be per mole, M-O-L. Okay. They do have H values in terms of grams. You can calculate it yourself or you can look it up. But most homeworks, software packages, exams, etc., have it in terms of moles. So I want to train you according to that expectation. Okay. All right. And let's talk about ice. Ice is going to have its own C value. So the C value of ice is 2.09 joules per gram degree Celsius. Okay. So we have 2.09 on the left, 6.01 in the middle, or the second one, and then 4.184 in that middle one. All right. Let's go to the vaporization or condensation. The H of vaporization is, now look out for this gigantic number, 40.67 kilojoules per mole. Okay. These numbers don't mean so much by themselves. They mean more when you compare them to each other, in my opinion. This is wild to me. I mean, this says a lot. This shows how strong a hydrogen bond is. To loosen the hydrogen bond, about 6 kilojoules for a mole of water. To break the hydrogen bonds entirely is going to take another 40 kilojoules, okay, per mole. So to break hydrogen bonds completely, in one sense, would be 46.67. They just show it. This is like, 8 times that number, 7 or 8 times. All right. It's crazy. So that's why we have this long runway. It takes a lot of energy to vaporize. The final value we need is for heating up steam. And so the C value for steam is 1.86. And now we're back to regular joules. And that's over grams times degrees Celsius in the bottom of the units. Okay. So those are our 5 thermodynamic values for water. And again, these are provided. Okay. I think one more thing worth pointing out, ice and steam, in my opinion, those are very similar numbers, this 2 and that's like almost 2. So heating up ice versus heating up steam is about the same amount of energy cost. But if you look at liquid water, it's double the energy cost compared to heating up ice or steam. That's why this slope is not as steep. Because it takes more energy heated up, it's more stubborn in changing its temperature. Okay. And that's our phase diagram. Okay, so what we're going to do today, we're going to calculate 3 different things, all for the same block of ice. Okay, I'm going to use my favorite value of water, which is about a can of Coke. Okay, a can of water, 12 ounces, that's about 355 grams of water. We're going to start out with this can of water as a block of ice, as if someone had left their can in the freezer. Anyone's done that? Okay, you want to chill a can. And it's at room temperature, right? You're like, oh shoot, I forgot to chill it. And then you put in the freezer and then you forget about it. And then the can exploded and broke, right? From the expanding water. So we're going to have that can frozen. We had it in a freezer at -20 Celsius. We're going to bring it to the melting point. So that's going to take some amount of heat. We're going to melt it. And then we're going to bring it to a boil. Okay, so we're going to go from -20 through the melting point and then right up to the boiling point. So we're going to have 3 different calculations that we can do for this frozen can of water. Okay. All right. Yeah. All right, let's go ahead and get started on that. Okay. So we're going to pose it as 3 different calculations. Okay, so today's example. Okay. Okay. We have our H2O can. And it's at -20.0 degrees Celsius. Okay. A modern freezer in a home in Celsius, about -10, -20, depending on the manufacturer, Celsius. Okay. And we have 350 grams, 355 grams of H2O. And right now, it's a frozen block of ice, essentially. Okay. Ice got that sheen on it. Okay. All right, we're going to bring it to 0.0 degrees Celsius. Okay. So we're going to heat it. Then we're going to melt it. And then we're going to go to 100.0 degrees Celsius. Okay. We're going to have our liquid water. And we're going to heat it some more. And there's 3 different heats that we're going to calculate. We're going to calculate the amount of heat required to heat the ice. So we're going to call that Q ice, or maybe Q1. Okay. Then we're going to calculate the heat required to melt the ice, Q melt, or Q2. And then we're going to calculate the amount of heat required to heat the liquid H2O, LH2O, Q of LH2O, or maybe we'll call that Q3. So we're going to calculate all these Qs. And then to figure out the total energy required to take the ice from -20 through the melting point all the way through 100, okay, you will just simply add up all of the Q values. Okay. And just to warn you, some problems are sneaky. Okay, some problems, I could have phrased this problem even without the word melt. I could have said, hey, how much energy does it take to take ice? Or I could even just said water. Hey, how much energy does it take to take water from -20 to 100? I didn't even use the word ice there. I didn't even use the word melt. I didn't use words like liquid. Okay, I just said water from -20 to 100. You would have to recognize that you have 3 different processes you'd have to calculate. Okay. We'll just do 3 today. When I was a newbie teacher, I thought I was cool and gung-ho by having us do 5 in one class, and people were getting fidgety in their seats. So I think you all can figure out how to do 5 in an example. I think 3 is enough for today. Okay. All right. So that's going to be the example. We need the mathematical foundation for calculating this. So I'm going to introduce 2 equations. Okay, one you know from lab already, or at least hopefully learn from lab. If not, I'm just going to re-say it. That's the Q equals MC delta T. And then I'll introduce the other one. Okay, so let's talk a bit about heat calculations. All right, heat calculations. There are 2 kinds that we do in Chem 101, and just 2 main ones. All right. The first category is going to be temperature changes. Okay. And then I'll leave maybe 5 or 6 lines of space to write the equation. I'll get back to it in a moment. And the second category is going to be structural changes. Okay. 2 categories of calculations, therefore 2 different equations. Okay. All right. So for temperature changes, your formula is going to be Q equals MC, and then capital Greek letter delta, in Greek, that's their capital D, delta T. Delta is not a variable. It's not a letter. Okay, it's not a constant or anything. Delta just means final minus initial. Okay, final minus initial. It just means change. How much did your temperature change by? And the only way you can calculate a change is to subtract the difference. Okay. So if we're talking about a delta T, that means we're going to take our final temperature and then subtract our initial temperature. Okay. So that's delta T. So I like to calculate my delta T's on the side before I plug them into the equation. Okay. And yeah, I would provide this formula. Okay. Every once in a while, I have a student studying for a medical career. They want to go to medical school. So some people nickname this equation Q equals MCAT. MCAT is the name of the medical exam they have to take. Okay. All right. And let's make sure we're on the same page as far as what the variables mean. Q is going to be heat energy, which will be joules or kilojoules. M is mass. That's going to be in grams. C is something called specific heat capacity, which is a mouthful. Okay. Now, specific heat capacity is just how much heat something needs to absorb before its temperature changes. Okay. How much heat can you absorb? How much heat do you need to absorb to change your temperature? Okay, that's specific heat. I like to nickname this heat ability. The heat ability of something. All right, so in lab, you were measuring the specific heat for glass and some unknown metal. Okay. Water specific heat's like 1 calorie for liquid water. It's like 4.184 joules, right? In lab, we saw that the calorie specific heats were much lower. Okay, metals heat up way more easily. They don't take as much energy compared to molecules like water. Okay. Specific heat is going to have units of joules per gram degrees Celsius, or in lab, you had calories. Okay, for today, we're going to stick with the joules. And if you want to write a definition for these units, it's the amount of heat required to take 1 gram of substance up by 1 degree Celsius. To heat something up by 1 degree Celsius, 1 gram of something, how much energy do you need? Okay. And that's a specific heat. Okay. And it's that specific heat that is the main workhorse of this equation. Okay, and then the final variable is going to be your delta C, and that's going to be in degrees Celsius. Okay. So that's your temperature change formula. And again, this is your main workhorse of the formula. Okay. You don't have to memorize a million specific heats. Those are provided to you. Okay. So that's the first equation. Notice this is a mass-based equation. We need a mass, the M, in order to calculate. For the structural changes, we usually like to think about that in terms of moles instead of by mass. And because of that, we're going to need a slightly different equation. Okay. And so N is the first new letter you're going to see here, and N is going to stand for moles. Okay. So we're going to be calculating water, right? So we have to figure out how many moles of water we have. Then H is our other new letter. And get ready for a new word. This new word is called enthalpy. That sounds weird. Yeah. I've never heard the word enthalpy outside of chemistry or physics. That's spelled E-N-T-H-A-L-P-Y, enthalpy. Okay. And to describe what enthalpy means, maybe it's better to give you the units for it first. Okay. It's going to be joules per mole, or more commonly, actually, they'll write kilojoules per mole. So I'll circle that one. All right. Okay, so comparing specific heat versus enthalpy, you'll notice that specific heat has 3 different units in it. It has energy, and it has the amount of substance in the form of grams, and it also has a temperature, okay? But notice when it comes to a structural change, there's no change in temperature. There's no temperature anywhere in this formula. In a temperature change, yeah, by definition, you're going to have a change in temperature, okay? When you have a structural change, there's energy absorbed or released by the change in structure, but it doesn't involve any change in temperature, okay? I used that word latent heat earlier. These are latent heat processes. And when you have a structural change, you're absorbing or releasing heat, but you don't really notice it so much in the temperature, okay? Often you don't notice it at all. All right. So there's 2 main types of structural changes. Okay. There's phase changes. And that's the type of structural change we're talking about today. Okay. Like a temperature change, a phase change is also a physical change. Temperature changes or phase changes, they're just physical changes. We're not doing chemistry. Okay, we still have water. We just change how the water is arranged, the structure. Okay. There is a second type of structural change we'll study later in the course, potentially, if we have time. And that's a chemical change. Okay. When you have chemical changes, there's energy released from the chemical reaction. And when you release that or absorb that energy, that's going to be based off of how many moles of the reactant you had. For example, if you're burning gasoline, how much heat is released as a result of burning the gasoline? Okay, you would have to figure out how many moles of gasoline you have. Okay, so chemical changes uses the same exact math as a phase change. Okay. But for today, we're just going to stick with the phase changes for water. Okay. Again, since it's a latent heat process, there's no temperature change. You don't see temperature anywhere in there. And so you need the moles, and then you need the enthalpy of the phase change, which is kilojoules per mole. And you can see the moles and the moles cancel out. Okay. So like everything I say in chemistry, ultimately, once you know what you're doing, it's just a matter of canceling units, doing plug, chug, all the usual stuff. Okay. Yeah, so if we take a quick back of the diagram, you can see that the H, the enthalpy, that's what's involved in the phase changes. That's why I gave H values. Okay. So yeah, those are your 2 equations. Again, I provide them. You can try to memorize them if you want, but basically, as with everything, if you know how to cancel the units, then you're good. Okay, let's go back to the problem at hand. Okay, we're gonna calculate Q1, Q2, and Q3, and then add them up together. All right. So part one, we're going to take 355 grams of ice from negative 20.0 degrees Celsius. And we have to take that to the freezing point of water, or the melting point. Okay, how much is Q1 for heating ice? Okay, we'll do this one together. All right, so for Q1, actually, before I just give the answer, I want you to think about which equation we need. Okay, for heating ice, do we need Q equals MC delta T? Do we need Q equals NH? Which one? Okay, think about for a moment. Are we doing a temperature change? Are we doing a phase change? You betcha. So since we have a phase change, we'll use that formula. MC delta T. Okay. All right, I like to do my delta T separately before I do my plug and chug. So we have to do T final minus T initial. All right. Go ahead and calculate that delta T and make sure you're really, really, really paying attention to final minus initial. I say the most common problem in these equations is people actually usually do the math correct, and that's good. But, excuse me, people often get the signs wrong when they're feeling anxious, okay? My cure for the anxiety is just follow very, very strictly finding out what your final is, finding out what your initial is, and doing final minus initial.
This is just
The delta T. Yeah, which we're going to plug into there. Okay. And if you have a negative, if you're subtracting a negative, remind yourself that that turns into a positive. Okay. So we have 0.0 minus negative 20.0 degrees Celsius. And minusing a minus turns into a plus. So we're going to end up with positive 20.0 degrees Celsius. Okay. When I was learning about subtracting negatives, one thing I would do is I would pretend that this negative sign went on top of the other negative sign and looked like a plus sign. I don't know if anyone else does that in their head, but I do that still to this day. I just, and it looks like a positive. All right. So we got that, and now we can plug into that. All right, let's get all the numbers. We have 355 grams of ice, and we're going to multiply it by the specific heat of ice. So we have to really, really, really make sure we're plugging in, we're pulling the correct of the 5 different values provided. We need the 2.09. And then we lastly multiply by the delta T. All right, I get 14,839 joules. Okay. Now each of those numbers have 3 sig figs, so I'm going to round in accordance to sig figs, and that'd be 14,800 joules. When we add up Q1, Q2, Q3 together, I suppose you could carry the extra digits to minimize rounding error, but I'm not going to make you do that. All right. Now, if we wanted to turn this into kilojoules, what's some math we could do? I mean, I could write out the dimensional analysis, but if you remember, kilo means 1,000. If we divide this by 1,000, we'd get 14.8 kilojoules. Okay. To save time, I'm not going to show that process. We've done conversions a lot. You're going to see how in the end, keeping everything in kilojoules will actually make our math much easier. Okay. And that was the part one calculation. How much heat does it take to turn the ice or to turn the ice from -20 to 0 Celsius? Heat the ice as much as possible until it's just ready to melt. All right, let's go to part two. I think I can fit this onto the same page. We need to take 350 grams of the ice, and we have to turn it into 355 grams of liquid water. Okay. And we have to figure out the energy required for this process. Okay. So for phase changes, this is where we take out Q equals, what's Q2 question mark? We're going to do Q2 equals N and then H of fusion. Okay. All right. So we have the H of fusion, 6.01, but hold up. What's grams or moles? Moles, right? We don't have moles. So we have to do a little bit of busy work. Okay. So gram to mole busy work. We have 355 grams of ice. And I think probably some of you by now have water's molar mass memorized. We've used it a lot. Anyone know it offhand? Water's molar mass. Right on. Okay. So there it is, 18.02. Boink. And we get 19.7 moles of water or ice or whatever you want to call it. Okay. And now that we have the moles, we can go ahead and finish the calculation. We're going to take 19.7 moles of water, and we're going to melt it, unfuse it. That's going to take 6.1 kilojoules. And we get 118. There's a 0.399, but 3 sig figs again. So I'm just going to stop it at 118. And we have kilojoules. All right. And then go ahead, if you haven't already, confirm you get the same number on your calculator. Nice. Okay. All right, right on. Okay, so hopefully now you can kind of see why I took our part 1 answer from joules to kilojoules, because I just thought it'd be easier once we had to add them up. We don't have to think about units anymore. All right, we've done a temperature change, we've done a phase change. Now finally we have a part 3. And we're going to do 355 grams of liquid water from 0.0 degrees Celsius to right up to the boiling point. Okay. We'll call this Q3. All right, go ahead, take 3-5 minutes or so and calculate this one. I'll leave this one to you, and then we'll go over it in like 3 to 5 minutes. Water break back. I don't know. They both went to the bathroom. That she did tell me. Like, it's changed last fast. Yes. All right. I'll walk it out. Oh, thank God it's Friday, man. I'm sleepy. How we doing?
Right.
All right. Figure out which formula first, the MC delta T or the NH.
Okay.
And you have to ask yourself, do we have a temperature change? If so, you want to use the MC delta T. If we're melting or vaporizing something, we're doing a phase change, you want the NH. How we doing? Hey, look at your phone. That one, yeah? Yeah. You've seen this stuff before. Yeah, same old, same. In Chem 112, you're going to add entropy. It's not just going to be heat only, but you're going to think about the statistics side of thing as well. It's still plug and chug at the end of the day. All right, quick show of hands if you want another moment. All right, we'll just dive in then. All right, so let's do the delta T first. Okay. Again, people get the signs confused. I saw in my other class, they're like getting negative 100s, negative 20s. Okay. It helps to do the math for sure, but it also helps to kind of like think about it, maybe even out loud. Okay. We're going from 0 to 100. Okay, that means we're raising the temperature, and we raise the temperature. That means we're gaining temperature, we're gaining heat. Okay, so it should be a positive number, hopefully at that intuitive level. Mathematically, we get 100. Okay. Now you can see why Celsius is nice. Celsius is nice because you have moments like this where the calculation is super slam dunk. Okay. All right. Yeah. So, all right, we're gonna use the grams or the moles. M is 4 moles. So Q3 is going to be the M of liquid water, C of liquid water, delta T of liquid water. All right, so we go 355 times which one? Yep, 4.184. In some books and homeworks, they won't write that last 4. I wouldn't worry too much if it's there or not. Joules over grams, degrees Celsius. And we got a delta T of 100.0 Celsius. Okay. 3, 4, 4, we're going to have 3 sig figs on this answer. Okay. I always like to point out unit cancellation. There's a reason why I spent all the extra class time writing out all the boring units so that you can see how things work. All right. 148,532 joules. Okay, with correct sig figs, that's going to be 149,000 joules. And might as well just get those into kilojoules immediately as well. All right, everyone getting that same number? All right. Was that heading on? The time of day, I'm starting to second guess myself. I've been eating healthy and less and like exercising a lot these past 2 weeks. I get these cravings for like burgers and Totinos and junk food. And no. It's the worst when my kids, they're just like, and like they don't gain any weight or nothing. That was me back in the day, but 149, yeah. All right, and we're almost done. Okay, so the ultimate question, the question we asked at the beginning is, hey, how much heat does it take to take some water from negative 20 to 100? We covered all 3 processes that happen, so now all we gotta do is just add them up. Okay. So Q total, we're gonna just add up Q1, Q2, Q3. Okay. And we didn't do it today, but we had a hypothetical silly problem of, there we go, going from ice all the way through steam. You would have 5 calculations. Okay. But we just stayed 1, 2, 3. All right. So let's line up them digits. And we got a 14.8. We get a 118. And 149 kilojoules across the board. All right. And from a sig fig standpoint, I'm starting to like the term significant digits over sig figs. I don't know, I've had a change of heart. Our last significant digit is in the ones place. So that's where we're going to end our significant digits, all right? 14.8 plus 118 plus 149. Enter. All right, 281.8. But again, our sig figs, sig digits end in the ones place. So this rounds up like the weed killer to 282 kilojoules. Okay. And that's a positive number, which makes sense because we were absorbing heat the whole time. Okay. Said another way, if we had done the opposite calculation, then everything would be the negative versions of all those answers, and we would end up with negative 282 instead. If we were going from 100 Celsius water down to making it into an ice cube, down to keeping that ice cube at negative 20. Okay. All right. With the last 5 minutes, I wanted to just, I think, we all had lab already this week. So you've probably gotten a flavor of how to do some of those lab calculations. And I know those of you who had me with lab on Tuesday, you've already turned it in. But for the remainder of you, okay, just wanted to point out some things. Okay. So earlier we talked about the equation of temperature changes, Q equals MC delta T. Okay. If we are combining two substances with each other and have them equilibrate at the same temperature, you have a special ability of finding out the specific heat of some unknown material. All right. And that's what you all did in lab. Okay. So in lab, you found the specific heat for an unknown. And we do that through a heat transfer. Okay. So you heated up the beads. Okay, you got them to a hot temperature and it has a certain amount of heat in it. Then it transferred heat to the 20 grams of water you had in the coffee cups until the heat transfer was over because they ended up at the same temperature. Okay. Heat transfer can only occur when you have a difference of temperatures. Okay, when the temperature is the same, it's over. So the amount of heat given from the beads is equal to the amount of heat received by the water. Okay. Now I have to put a negative sign here. Okay, to be technical. So I'm going to circle that negative sign. Like, wait, what? It's the same amount of heat. And you're right. But when you're doing mathematics, we are often not working in absolute values. We're often working with whether you gained or lost something. And when it comes to heat, you have to really track gain or loss really precisely, okay? And especially some of you are thinking about like engineering careers and such, like that positive and negative signs is really important. That's where everyone gets the thermo questions wrong, okay? So let me use my favorite example. Well, food's my favorite example. My second favorite example is money, all right? So if I give Gentry $100, okay, you have gained $100, and I have quote unquote gained negative $100. Okay, I'm down $100. Notice 100 is not equal to negative 100. In order to make the two sides equal, I have to put a negative sign in front to negate the effects of the negative side. Okay, so that's why there's negative sign here. So the amount is equal, but the sign is different. We just put that negative sign to undo the effects of the sign. All right. So what we did in lab is we do a substitution of variables to get the final equation. Earlier, we wrote Q equals MC delta T. If we substitute MC delta T for Q, we're going to end up with the M of the beads, the C of the beads, the delta T of the beads, and that's equal to the negative mass of water, the C of water, and the delta T of water. Okay. All right. And we were interested in the specific heat of the glass or of the metal. So to isolate that C, we just take the M beads and the delta T beads on both sides. Okay. Those cancel. And we end up with this sort of formula. Okay. Some professors, I know like Professor Jacobson, for example, she has people calculate that Q entirely separately and then plug into there. That works too. And then make sure for a denominator with multiple components, you use parentheses, and there is that negative sign there. Okay. When I walked in, I saw like some of you had already calculated this out, but if you haven't done it yet, I wrote a color-coded board diagram in the lab. Hopefully most of you saw that. But your mass of water, you weighed about 20-ish grams. Your C of water is always 1.00 calories over a gram degrees Celsius. Your delta T of water was somewhere around 10 to 20 degrees Celsius. Your mass of beads was around 30 grams for glass. And for your metals, it was like maybe 60 to 120 grams for your metal. And your delta T beads was somewhere around maybe negative 40 to negative 60 degrees Celsius, okay? With those negative signs. Negative signs will cancel, so you should get a positive number. So you can use a negative sign twice in your calculator, or what I do is if I know they're going to cancel anyways, I don't even bother to type negative signs. Okay. All right, and then you use page 6 of the handout to compare your density and specific heat values. Okay, I strongly urge you to use common sense when you do the calculations. Okay, some of the specific heats are similar, some of the densities are similar, but for your unknown metal, there's that old saying, lightning doesn't strike twice. If you have two similar densities for two unknowns, it's going to definitely be different in terms of a specific heat. Okay. All right. So that's about it. Go ahead and pack up. Have a great weekend. Good luck on the test. You haven't done it yet. And please, no one put platinum for your unknown. We're the second lowest tuition. You know what I mean? Like, no one put sodium. You would have caught fire and died. All right. All right. Low weekend.